because now FinFET is 3D, then you have a lot of orientation to worry about. So let's recall what we learned in lecture 5 about silicon crystal, right? We won't go into detail. I don't expect you to understand everything in detail, but I hope you agree that we have different orientation. Last time I showed you that as fake example. If the lattice is so sparse in this direction and so close in another direction, you will have different transport probability, different effective mass, etc., right? So they are anisotropic. So for silicon, you have 6 delta valley, right? We call this, we have 6. If you heard about this before, yeah. So I used to make a joke, where is Silicon Valley, right? It's the 6 delta valley. So because in silicon, you do have 6 valley. That you have the lowest energy, this is in the momentum space. But anyway, just know that the electron can reside in this 6 location and in momentum space, right? And then during the transport, for those with high curvature, you have low effective mass. Those low curvature, you have high effective mass. So for the electron, for example, here, transporting in the x direction, you have a longitudinal transport along this low curvature direction. So you have a high effective mass, which is 0.98 of the rest electron. On the other hand, if you are transporting in other direction, let's say Z or Y for this set, then you have 0.19. Right? So similar for this one, when you transport in x direction, because the curvature in this direction is high, so you have 0.19 effective mass. Okay? So the message is that you have 2 different types of effective mass, 0.19 and 0.98 in different direction. Just remember this, that is enough. So if that is the case, now your FinFET is very funny. It is 3D standing up. So I can actually have my fin rotating in different direction, right? So in this particular example, it says that in this direction, it is 110. So let me finish this and the next slide, right? So what does it mean? Then it means, let me just draw it, that will be easier. This is 100, and this is 010, for example. Okay, so as a result, here is 110, or here is 110, right? So we don't care about how exactly I put the number, right? Because 110 and 101 are just equivalent. It doesn't matter, right? So if you look at this fin, this one, if I had a pattern here, so the fin is in this direction, is 45 degrees to this 110, then it means this surface is perpendicular to it, is 100. Okay? Now, when we put it in the, and then if this is source, this is drain, and then the electron is transporting in this direction, what is this direction? This direction is also 100 because you are transporting in this direction, okay? This surface is perpendicular to this one. Let me make this clearer. This surface here is 100, right? And then for the transport direction, this here is 100. So the surface, okay, surface, we usually will use parenthesis, and then the direction, we use angular bracket. So, okay, so when I say that the electron is transporting in 100, I will use this one. But yeah, you're transporting in this direction, but what surface do you have? It can be any other surface, right? Yeah.
So going back to the momentum space diagram, how do the surface and so
the direction correlate to this one. Is that okay? Because maybe I Yeah, the direction of the crystal. For direction, right? Because when we say X, Y, Z, they're talking about 1, 0, 0, what, 0, 1, 0, and 0, 0, 1. So they are equivalent, right? They are all going up here or here. But I can transport in 45 degree. Then this is 0, 1, 1, right? That is the direction. Now, surface is what? Because you are doing a transistor, you have an inversion layer, you have an oxide and also the silicon dioxide. That is a surface. So yes, I'm going in this direction, but what is the interface next to me? The interface can, right? For example, how to do that? I'm transporting in this direction. The interface can be, and then if I try to do this as like looking into this direction, right? This is the eye. How do you draw the eye? This is the eye, right? I'm looking into this direction. Then I get this one, right? The surface can be here, can be here, can be here, can be here, right? Because this is the silicon dioxide, silicon dioxide. You can have different surface, and each of them has one orientation. Do you see what I mean? Transport direction is into the screen. Are you okay? Yeah. But surface can be anything surrounding me, right? Depends the orientation of the transistor. And that's why this guy is transporting in 1, 0, 0, but the surface is 1, 0, 0 also. If I have like 45 degrees, it's still transporting at 1, 0, 0, but if I cleave this by 45 degrees, then the surface is 1, 1, 0. Make sense? Okay. So because of this, then the mobility of FinFET has the dependence that highly depends on not just the transport direction. Let's look at this. 1, 1, 0, right? And then this is the surface. So you need to mention whether it is its transport direction and also the surface direction. That is the only thing I want to show here. This is the transport direction. And this is the surface direction. So, okay, when you read this graph, and it turned out that for electron, is the fastest when you are transporting in 1, 1, 0 direction, but on the 1, 0, 0 surface. Hole is the fastest in 1, 1, 0 direction, but on the 1, 1, 0 surface. Okay, analogy is that say, okay, you are the fastest, you transport into the screen, but for electron, maybe your interface need to build in this way, and for hole, you may need to build in this way. Okay, because of time, I will just stop here. Okay, let me know if you have any questions.